Welcome. So, in the totally wild world of subatomic physics, some particles are so ridiculously unstable, they don't even have one single fixed mass. Which raises a huge question, right? How in the world do you do the math on that? Well, today, we're going to pull back the curtain on a really clever trick physicists use to solve this puzzle. It's a tool they call the narrow width approximation.
So let's just start with that puzzle. Seriously, think about it. Imagine you're trying to weigh something. But instead of having one single weight, it has this whole range of possible weights. How would you even begin to do calculations for that? And this isn't just some abstract thought experiment, It's a real, fundamental challenge that physicists at places like the Large Hadron Collider have to deal with every single day.
Okay, so the problem really starts with these incredibly short-lived, fleeting particles. A great example is the W boson. It's one of the particles that carries the weak nuclear force. These guys, they just pop into existence and then decay in a tiny fraction of a second. They just don't live long enough to have what you'd call a perfectly defined, stable existence.
Now, because of that super short lifespan, a really strange rule of quantum mechanics kicks in. And it basically says this: the shorter a particle's life, the more uncertain its mass has to be. So its mass ends up being kind of fuzzy. It's not a single sharp number you can write down. It's more like a range of probabilities.
So to actually describe this fuzziness with math, physicists use a special tool. It's called a Bright-Wigner propagator. Honestly, the best way to think about it is like a blurry photograph. You know the particle is there, you can see its shape, but its mass isn't in sharp focus. Instead, it's kind of spread out over this curve of possibilities.
And you can probably guess what comes next. Trying to do calculations with that entire curve, this whole continuous distribution of every possible mass, is a total nightmare. I mean, it is computationally massive. It's the kind of thing that can bring even the world's biggest supercomputers to their knees. It's a huge roadblock when you're trying to make predictions.
So you're faced with this just overwhelming complexity. What do? Well, physicists came up with an incredibly clever solution, a really elegant simplification that works like a perfect shortcut.
And this right here, this is the core idea. On the left, you've got the complex reality, that messy, fuzzy Bright-Wigner curve. And on the right, that's our shortcut, the narrow width approximation. It basically just asks, hey, what if we just pretend the particle has one single mass, right at the very peak of that probability curve? You trade that whole messy curve for one simple point, and suddenly the math becomes totally manageable.
All right, so how does this shortcut actually work, mathematically? Don't worry, we are not about to get lost in a forest of equations here. We're just going to focus on the really clever concept that makes the whole trick work. Here's the crucial move. The NWA formally replaces that wide, blurry, Bright-Wigner curve with something called a delta function. Now, a delta function is this perfect mathematical idealization. It's a spike that's zero absolutely everywhere except for at one single point, and at that point, it's infinitely high. So what you're doing is, you're basically forcing the particle to have one exact mass with zero probability of having any other. And the direct result of this mathematical swap? You get a sharp mass distribution of the decay products. What that really means is, instead of the debris from the particle's decay having this spread of energies, it all comes out as if it came from a parent particle that had one single, perfectly defined mass. Everything gets neat and tidy.
But look, it's a shortcut, and like any shortcut, it has its limits. This is an approximation, it's not the full reality, and if you use it in the wrong situation, well, you can run into some pretty big problems.
The source material puts it pretty bluntly. If you use this approximation where it doesn't apply, it, quote, may yield unphysical results. And that's a physicist's way of saying your calculations will spit out answers that are just plain wrong, answers that literally don't make sense in the real world. So, when does it all break down? Well, here's the kicker. The approximation fails when your experiment or your measurement is so precise that it can actually see the fuzziness of the particle's mass. Think back to that blurry photo. If your camera is so good that you can actually see the blur, you can't just pretend the picture is in perfect focus anymore, right? And lucky for us, physicists have a really handy rule of thumb for this. It's a simple check. First, you find the particle's width, which is represented by that Greek letter gamma, and it's just the technical term for its mass fuzziness. Then you find its average mass. If the precision of your measurement is better than the ratio of those two numbers, the width divided by the mass, then you're in the danger zone. The shortcut is probably going to fail you.
So you see, it's all about a trade-off. The pro is massive. It makes incredibly complex calculations way, way simpler. But the cons? they're serious. It's not just about getting unphysical results. This shortcut can actually make you ignore important physical connections between particles, basically losing some of the fine detail in the process.
So with all these limitations, you might be asking, why is this so important? I mean, why would we use a tool that we know can sometimes be wrong? Because the narrow width approximation isn't some kind of cheat. It's an absolutely essential tool. It really gets to the art of what it means to be a physicist. It's about knowing when you can make a smart, reasonable simplification to get a really good answer without getting hopelessly bogged down in impossible complexity. It's all about understanding the limits of your tools so you can explore the fundamental laws of nature.
And that kind of leaves us with a final thought, doesn't it? We've just seen how scientists will sometimes make a perfect assumption, like a single exact mass, to help them understand a really messy and complicated reality. So what other idealizations can you think of? Not just in physics, but in any field of science that we use every day to make sense of our beautifully complex world.